Hi, I am Dr. Shyam Sarkar. Welcome to my class. Don't forget to subscribe this channel for more updates. So this is lecture 2 for chemical bonding. Here we will discuss the limiting radius ratio calculation for different coordination number. For example, coordination number 8, that is for cubic system, coordination number 6, that is for octahedral system, and coordination number 4, that is tetrahedral system. Okay, so I will show the details calculation for the limiting radius ratio value. Then I will go for the few question answer discussion on radius ratio, and finally I will end this lecture by packing of ions, and I will show the different types of crystal packing with example and corresponding the three-dimensional diagram. Okay, so I would request all of you just watch my previous video on chemical bonding, where I have discussed about ionic bonding and general characteristics for ionic compounds and different types of ions, size effect and radius ratio. Radius ratio rule I have discussed there, and the application and limitation of radius ratio rule. So I have shared the video link for the previous lecture, that is lecture 1 for chemical bonding, in the description of this video. Okay, you may watch the previous one, then it will be easier to understand this video. Here I have shared this chart of radius ratio, where I have shown the limiting radius ratio values in the left side, then the coordination number and corresponding structural arrangement with few examples. Okay, so here you can see the limiting radius ratio value for 8, that is cubic coordination number, that is 0.732 to 1. So I will show you how these values, that is 0.732, 0.414, 0.225 are coming. So first, if you see this question here, calculate the limiting radius ratio for 8:8 coordination number. Okay, or sometime it may also ask like this: calculate limiting radius ratio for cesium chloride crystal, because we know that cesium chloride is the characteristic of 8 coordination number cubic structure. Okay, so let us see how to calculate the limiting radius ratio value. That is, we know that for cubic system it is in the range from 0.732 to 1. So I'll show you how this 0.732, this value is coming. Okay, so if you see this three-dimensional structure of cesium chloride, now you see this. If you see from the top, you can see we can simplify this system for our calculation in this way. So this is the representation which we will use for the calculation. See here, the structure of cesium chloride shows that each cesium ion is surrounded by 8 Cl- ions, and vice versa. That means each Cl- is also surrounded by 8 cesium ion. Okay, now see, to get as close to cation as possible, that means they will be just touched to each other. So anion must touch to along the edge of the cube, as shown in this figure. If you see this figure, all the anions are touched to each other, and with the corresponding cation also. Cation is also touched with all the 4 anions. Here I represented the cation is in the yellow color and anions are represented in this magenta color. Okay, so the sides of the cube, if you see, sides of the cube has a length a, where a equal to 2r minus, because if you see r minus and r minus, radius of the anion, if you combine this r minus plus r minus, that is the side of the cube length, that is a here. So now if you see the along the body diagonal, the cesium ion is touching the 2 Cl- on either end, so its length d. So d equal to r minus plus r plus plus r plus plus r minus. So if you see this diagonal, that is r minus plus r plus plus r plus plus r minus, so it becomes 2r plus plus 2r minus. Okay, now if we use the Pythagoras theorem, then the length of the side and the body diagonal of the cube are related as d square equal to a square plus a square plus a square. That means d square becomes equal to 3a square. That means 3 into, we know that value of a is 2r minus. So if you put the value of a equal to 2r minus, so it will become 3 into 4r minus square. Okay, that means 12r minus square. Now if you calculate the value of d, so d equal to becomes 2 root 3 r minus. Okay, now see, if you know that relation 2r plus 2r minus is d, so if you put the value of d here in this equation, so 2r plus and plus 2r minus equal to 2 root 3r minus. So if you calculate the ratio, that means if you divide it by r minus in all these, so r plus by r minus becomes root 3 minus 1. That means 1.732 minus 1, that is 0.732. So this is very simple calculation. In this way you can get the limiting radius ratio value for cubic system, that is for cesium chloride system, that is for 8:8 coordination system, or simply for 8 coordination system. You will get the limiting radius ratio value is 0.732. Okay. So next one, similarly I will show you the calculation for octahedral, that is 6 coordination number and 6:6 for cation is to anion. Okay, here also question comes like that, calculate limiting radius ratio for NaCl crystal. So here if you see this structure, so this is the representation from the top view. If you see from the top of this three-dimensional cube, so it looks like this, and for sake of simplicity we will consider cation and anion in the similar pattern. Okay, so here you can see the structure of NaCl, which we know that each Na plus ion is surrounded by 6 Cl minus ion, and similarly each Cl minus is surrounded by 6 Na plus ion. Okay, so as shown in this figure, along with the cube edge, the Na plus is touching with 2 Cl minus ions. So its length A becomes here, in this case, A equal to r minus plus 2r plus, that means r plus plus r plus plus r minus. So similarly 2r plus 2r minus equal to A. Okay, now similar expression as just previous one, to get as close as the cation as possible, the anion must touch along the diagonal of a face of the cube. Okay, so if you see this, now this diagonal has a length d, where d equal to r plus 2r minus plus r plus equal to 4r minus here in this case. Now if you apply Pythagoras theorem, then length of the side and face diagonal of the cube are related as, see, d square equal to a square plus a square here, so equal to 2a square. Now if you calculate the value of d, so d equal to becomes root 2a. Okay, so we know that d equal to 4r minus. So if you correlate these two equations, we will get that 4r minus equal to root 2 into r plus 2 into r minus. Now if you calculate the radius ratio, that means r plus by r minus becomes root 2 minus 1, and root 2, we know that root 2 value of 1.414 minus 1, that is 0.414. So in this way you can calculate the limiting radius ratio for 6 coordination number, that is for NaCl like crystal structure. You will get the limiting radius ratio value is 0.414. This is also simple calculation, just simple geometry. So if you remember like this is the simplest way, and if you remember this, you will in exam you can easily solve this kind of problem. Okay, so next we will solve the similar kind of limiting radius ratio calculation for 4 coordination number, that is type of ZnS crystal structure. Okay, that means tetrahedral. Here in this structure you can see this is Zn2 plus ion is surrounded by 4 sulfide ion, and similarly 1 sulfide ion is surrounded by 4 zinc plus ion. Now this is little bit different from other two. Here see the calculation like this, the distance from the center of the tetrahedron to the corner D is represented by here d equal to simply r plus r minus here. Okay, now similarly, to get close to the cation as possible, the anion must touch along the edge of the tetrahedron in this case. So here distance a equal to r minus plus r plus. Okay, so r minus plus r minus, that means 2r minus. So the tetrahedral angle here, if you see, theta is denoted by theta, so theta is 109.5 degree. Okay, now if you take sine, so sine theta by 2 equal to r minus by r plus r minus. So if you put the value of theta here, so sine 54.7 degree becomes r minus by r plus r minus. So if you reverse this, so r plus r minus by r minus becomes sine inverse, that means 1 by sine of 54.7 degree. So if you simplify this, r plus by r minus becomes 1.225 minus 1, that means 0.225. So 0.225 is the limiting radius ratio for 4:4 coordination number, that is for ZNS type crystal structure. And if you correlate with the table I have just shown in the starting of this video, that is also 0.225. So this is proof that 0.225 is the limiting radius ratio for 4:4 coordination number and ZNS type crystal structure, that is for tetrahedral. Now if you see this question, this is very important question, it comes in university exam. Okay, so here they asked for, see here, HGS crystallizes in ZNS structure although it has the radius ratio of 0.68, explain. So you have to explain this kind of problem. Here see HGS, so it has the radius ratio 0.68, still it crystallizes in the ZNS structure. It should not be ZNS structure. If you see the value of radius ratio 0.68, so 0.68 falls in the limiting radius ratio is in between 0.414 to 0.732 range. So if you see this range 0.414 to 0.732 in the chart of radius ratio, so you will see that it should crystallize in the octahedral, that is in the NaCl form. Okay, so it should not form ZNS, but it crystallizes in the ZNS structure. So you have to explain why this is crystallizing as ZNS rather than it's not crystallizing as NaCl structure, which is evident from the radius ratio given, that is 0.68. Okay, so you will explain this question. So let's see how to explain this type of question. See, the limiting radius ratio for HGS, so for HGS is 0.68, so which indicates the Hg2 plus cation should occupy the octahedral sites. That means it should have 6:6 coordination number, that is it should form NaCl type crystal, but actually it forms ZNS type structure. Why ZNS structure is forming? So see here, owing to pseudo inert gas cation, that means if you see the electronic configuration of Hg2 plus ion, so it is just like a pseudo inert gas type of cation, and because of this it is highly polarizing, and also sulfide is there. So this is highly polarizing cation, that means Hg2 plus is highly polarizing cation, and sulfide of such polarizing cation is predominantly covalent. So this type of compound is becoming predominantly covalent rather than ionic. So due to this covalent nature, the anion becomes closer to each other than would occur in purely electrostatic attraction. So it is becoming more closer, which is not expected in case of ionic or where purely electrostatic attraction exists. Okay, so that's why this would initiate severe anion-anion repulsion in the expected octahedral structure. So if it is forms octahedral structure, that means if it goes for NaCl like structure 6:6 coordination, so there will be lot of anion-anion repulsion. So that's why this is not stable. So to get rid of such destabilization, the repulsion, the effective radius ratio decreased and Ag2 plus prefers tetrahedral site in ZNS structure featuring 4:4 coordination number, and this is the reason they form ZNS structure rather than NaCl structure. Okay, so this is the reason, because of covalency, and so they are just getting rid of this destabilization, that means just from the rid of anion repulsion, so they are forming this type of ZNS type structure. Okay, that means they prefers 4:4 coordination, although the radius ratio value, limiting radius ratio value 0.68, it does not tell, so it is telling that it should form NaCl structure, but practically just to get rid of this type of destabilization they are forming ZNS type structure. Okay, so this is the way in which you can explain this type of answer. Okay, so next we will see similar type of problem. Here if you see the radius ratio values for strontium oxide SRO is 0.81 and for barium oxide BaO is 0.96. so predict cesium chloride structure, but they adopt NaCl structure, explain why. So if you see the radius ratio, that is strontium oxide is 0.81 and barium oxide 0.96. See this type of value of limiting radius ratio which predicts cesium chloride structure, but they are not forming cesium chloride structure, that means they are not forming cubic structure, rather than they are forming NaCl structure, that is 6:6 coordination number, that is octahedral geometry. So rather than cubic geometry they are forming octahedral geometry. Okay, so you have to explain. So similar type of explanation just now I showed in the previous case, so I think this you can easily explain, so I just leave this question for you. Okay, you just try, just follow the previous one, you can easily explain this type of question. Okay, let us see this problem. Here they asked for, this is very important question, here they asked for why does KCl adopt the rock salt structure in spite of a radius ratio greater than 0.73. so it has radius ratio greater than 0.37, that means it should adopt cesium chloride structure because it is greater than 0.732. That means it's falling in the range of 0.732 to 1 limiting radius ratio. So it should adopt cesium chloride structure. In spite of that, it is crystallizing as rock salt structure, that means with coordination number 6 like NaCl structure. So there are certain parameters are given, like given RK plus, radius of K plus with coordination number 6 is 1.38 angstrom and with coordination number 8 is 1.51 angstrom. RCl minus is given 1.81 angstrom in both the cases, and Medullang constant for NaCl and cesium chloride structures are respectively 1.748 and 1.763. Okay, so let us see how to solve this type of problem. So see, the electrostatic potential energy is the main contributor to lattice enthalpy for any structure which is directly proportional to the Medullang constant A, and for that structure and inversely proportional to the intra-ionic distance D, that is D is represented by R plus plus R minus. So here in this case, if you calculate D for NaCl structure as well as for cesium chloride structure, you will get the difference. Okay, so let us calculate D value for NaCl structure if it adopts NaCl, and D if it adopts cesium chloride structure. So D if it adopts NaCl structure is 1.38 angstrom plus 1.81 angstrom, that means 3.19 angstrom. But if it adopts cesium chloride structure, then the D value becomes 1.51 angstrom plus 1.81 angstrom for Cl minus, and that becomes 3.32 angstrom. So now if you see the ratio of lattice enthalpies will be roughly equal to the ratio of from their respective electrostatic potential energies, that is from respective A by D term. So hence if you see the U means lattice energy, U NaCl, so That means for NaCl type of structure, lattice energy divided by U cesium chloride structure equal to A NaCl by D NaCl into D cesium chloride by A cesium chloride. So if you put the value of A that is given in the question and D we calculated in this just now, so if you put this value it becomes 1.03, that means greater than 1. So this shows the lattice energy for NaCl structure would be marginally more stable compared to the cesium chloride structure. That's why KCl adopts NaCl structure rather than cesium chloride structure, because the ratio of lattice energy becomes more than 1 and it prefers to the NaCl compared to the cesium chloride structure. So in this way you can solve this type of problem. So let's move to the next point, that is packing of ions. How packing of different crystal system occurs. So here I will show you one chart. See here different crystal structure and corresponding examples I have collected and just kept for you. You just go through one by one. See number 1, cesium chloride. So basic crystal structure is known as cesium chloride structure. So here see, if you see, I have highlighted in yellow color, that is the representation of this type of crystal structure because of this cesium chloride CSCl I have highlighted here. So this represents the whole crystal system. So whether it is CuZn or NBO or CsCN, so all these type of are the characteristic of cesium chloride. That's why I highlighted this name. So cesium chloride structure means it's not always cesium chloride, it could be CuZn or NBO or CsCN. So this is the representative name, cesium chloride structure, that is 8 coordination number, cubic system. Okay, so next one is fluoride structure. Fluoride means you have to understand that CaF2. So calcium fluoride, we know the name of CaF2, but this represents the general form of fluoride structure, which also example, there are many examples like PbO2, HgF2, UO2. These all are the fluoride structure, but main is the CaF2. So fluoride means automatically you will think CaF2 structure. Wherever you see fluoride structure, that means it is resembles with calcium fluoride structure. So CaF2 is the representative of fluoride structure. So number 3, perovskite structure. Perovskite means automatically calcium titanate, CaTiO3. So this is the characteristic compound of perovskite structure. That means this is the standard structure, one which we can say okay, this is perovskite. So similar to that, KMnF3, SrTiO3, BaTiO3, all these are perovskite structure. And next, the rock salt structure, fourth one. Rock salt means automatically you know the NaCl structure. So 6 coordination number, NaCl structure is rock salt structure. There are many other examples like KBr, AgCl, AgBr, MgO, calcium oxide. So all these are type of rock salt structure. Now next one, fifth one, rutile structure. Rutile means TiO2. So TiO2, there are many other phases also in case of TiO2, but mainly rutile structure means TiO2. There are other oxide like MnO2, SnO2, WO2, MgF2. So all these are belongs to rutile structure. So if you see the sixth one, zinc blende structure. So zinc blende is representative of ZNS. So ZNS cubic. So there are two types of ZNS. One is zinc blende and another is woodgite. So woodgite, and that is hexagonal, and zinc blende is cubic. So these two are different. You should not confuse with ZNS. So there are two types of ZNS. One is cubic and another one is hexagonal. Cubic means zinc blende and hexagonal means woodgite. Okay, so there are other examples like CuCl, CdS, HgS, INAS. So all these belongs to zinc blende structure, that means cubic form. Next, seventh one is spinel structures. Spinels means the general representative is MgAl2O4. So this is the standard compound for spinel structure, MgAl2O4. So there are many examples. Here I have shown only two, MgAl2O4, ZnFe2O4. So there are different type of spinel, that is normal spinel, inverse spinel. All these I have taught in CFT, crystal field theory, you have seen. So here just final structure belongs to MgAl2O4, and the last one woodgite means ZnS hexagonal is the representative compound, and other oxide also ZnO, BeO, sulfide, MnS, AgI, ammonium fluoride, all these are belongs to woodgite structure. Okay, so one by one I will show you all these different crystal structure in details, how their structure belongs. Okay, and what is the coordination number, what is their point group and space group. So first one is cesium chloride structure. Cesium chloride crystallizes in the cubic arrangement, and the cesium chloride structure is cubic with PM3M space group. Okay, so space group of this compound is PM3M, and the coordination number of both the cations and anion are 8. That means each cesium ion is surrounded by 8 Cl minus, and in the similar way each Cl minus is surrounded by 8 cesium ion. Okay, so cesium ions and Cl minus occupy the 8 corners of the cube, and the counter ion occupies the center of the cube. Okay, so if you see this diagram, see this three-dimensional diagram, so this looks like cesium chloride structure, how the arrangement of cesium and Cl minus, you can see all the cations. If you place all the cations in the 8 corners of the cube, and see center of this cube is anion, or reversely if you put the cation in the center, all the anions will be in the 8 corners of the cube. Okay, next structure is fluoride structure. So fluoride structure means, calcium fluoride, the representative compound here. So calcium fluoride crystallizes in the fluoride structure with cubic FM3M space group. Okay, now the coordination numbers are 8 for the cation. That means 8 fluorides ion form a cube around each calcium ion, and 4 for the anion. So here the coordination number of cation and anion is different. In case of cesium chloride it was 8:8, but here 8:4. That means cation is to anion is 8:4. So if you see, the 4 calcium ion is tetrahedrally arranged around each F minus ion. Okay, so many difluoride and dioxides are found with this type of fluoride structure, as you have seen in the chart I have just given. Okay, so if you see this structure, so this is the crystal structure of CaF2 type, that means fluoride type structure, where I have shown the arrangement of lattice arrangement of Ca2 plus and F minus, how they resides in a cube. Next one is perovskite structure. So perovskite structure is described by the characteristic compound calcium titanate CaTiO3 crystallizes in the perovskite arrangement. In the general chemical formula of perovskite compound is AbX3, where A and B are the two cations of very different sizes, and X is the anion that bonds to the both. That means both A and B. The A atom is larger than that of B atom. In the general, this is very general case, the ideal cubic structure has the B cation and in 6-fold coordination number surrounded by an octahedron of anions, and the A cation is 12-fold cubo-tetrahedral coordination number. So if you see this diagram, it will be very clear how the coordination number how cations and anions are just arranged in this type of cubic structure. If you see the coordination number, so A, B, X3 types of structure. So 3 different atoms are shown here in this way. Okay, so this is the perovskite structure. Next one is rock salt structure. This is very common. You all know that rock salts mean NaCl structure, and NaCl structure that is FCC, face centered cubic structure, and here the space group is FM3M. Okay, and coordination number you all know 6:6, very simple for rock salt NaCl structure. That means each cation will be surrounded by 6 anions, and each anion will be surrounded by 6 cations. So if you see the structure of NaCl, Here you can see each cation, that means each Na plus is surrounded by 6 Cl minus, and on the reverse each Cl minus is surrounded by 6 Na plus ion. So this is the simple structure of NaCl. Next structure, that is rutile structure. So rutile structure is TiO2 is representative compound. So TiO2 crystallizes in the three-dimensional crystal which forms an atmospheric pressure. Okay, so there are three different phases like anatase, bruchite and rutile. So rutile structure is a tetragonal structure with P42 by MNM space group. So this is the characteristic of this type of rutile structure, and the coordination number for this type of crystal structure is 6 for the cations. That means 6 oxide ions are arranged octahedrally around each titanium ion, and 3 for the anion. So 6:3 compound here. Okay, that means 3 titanium ion is trigonally arranged around the each oxide ion. So 6:3, 6 for the cation and 3 for the anion. So this type of compound belongs to 6:3 coordination number. The rutile structure are found in many dioxides of chromium, manganese, germanium, ruthenium, rhodium, tin, osmium, iridium, platinum, and in case of lead also. So there are a lot of examples with this rutile type of structure. Okay. So next I have discussed here zinc blende and woodgite structure. In both cases the representative compound is ZNS, but you should not get confused between these two structure, because one is cubic structure and another one is hexagonal structure. So zinc sulfide crystallizes in two distinct lattices, cubic zinc blende and hexagonal woodgite structure. In both compound, both this type of crystal structure, the coordination number is 4 for both the cations and anions, and the space groups are different. Okay, so F43M is for cubic and P63MC is for hexagonal. So two different space group exist for two different crystal structure. If you see the crystal structure looks like this. Next one is spinel structure. Spinels, there are two different types of spinel, inverse spinel and non-inverse spinel. I will not go to these details. Here I will just show how spinel structure exists. The spinels are the any class of minerals of general formulation, that is AB2X4. So which crystallizes in the cubic, that means isometric crystal system with the X anions, typically chalcogens, that like sulfur and oxygen, selenium, etc., arranged in a cubic close pack lattice. The cations A and B occupying some or all of the octahedral and tetrahedral sites in the lattice. So if you see the crystal structure here, representative crystal structure here I have shown. So this is the types of spinel structure. Okay, so in this way you can describe the spinel structure, and lattice arrangement here I have shown. If you correlate with this AB2X4, so this is the type of spinel. So this was today's discussion, where I have shown this calculation of limiting radius ratio of various system and packing of ions, how crystals are packed in different crystal system I have shown. Next lecture, that is in lecture 3, you will get some exciting lectures regarding lattice energy, solvation energy, and there will be lot of problems solved regarding this, and I will show the Born-Land equation of its derivation and application, and Kapuscinski equation, and there will be lot of problems related to lattice energy, because lattice energy is very important for any competitive exam like IIT-JAM, CSIR-NET, GATE, SET, and any kind of chemistry related competitive exam. You will get one must question from lattice energy. So wait for next lecture, so it will be uploaded very soon. Okay, till then stay tuned. If this video helps you, then don't forget to subscribe this channel and just put the like button, share with your friends, and comment if you have any doubt or any query. Thank you so much for watching this video till the end. Thank you for your patience and your cooperation.